Hi, this is S.Mastan, working as an assistant professor in Annamacharya University. Okay, today we are going to discuss a topic from data structures. The topic name is AVL tree. Okay, we are going to discuss on topic. The topic name is AVL tree from data structures. First of all, what is an AVL tree? See, we are having different names for this AVL tree. AVL tree is also called as a height balanced tree or self-balanced tree. Okay, first height balanced tree or self-balanced tree. First, we will see the definition. What is an AVL tree? AVL tree is a binary search tree. First of all, an AVL tree is a binary search tree. Okay, if you are thorough with binary search tree, no problem. Okay, we'll see simply an example. What is a binary search tree? Okay, what is a binary search tree means? See the definition. A binary search tree is a tree where all the elements of left subtree, all the elements of left subtree elements should be less than the root node. All the left subtree elements should be less than the root node, and all the elements of the right subtree should be greater than the root node. Okay, simple thing, nothing but if you take one root node, the left subtree elements which are on the left side of the root node should be less than the root node. Okay, and the same way, all the elements which are in the right subtree, those elements should be greater than the root node. Okay, we'll take one example here. We'll see one example. See, here we are having some elements are there. For example, we are having some elements 11, 6, 8, 19, 4, 10, 5, 17, 43, 49, 31. Okay, these are some of the elements. By using these elements, we are going to construct a binary search tree first. Okay, how to create a binary search tree? See here, first you can take any element as a root node. From these elements, you can take any element as a root node. First, I'm going to take the first element as a root node. See, 11. I have taken 11 as a root element. 11 as a root element. Okay, first, according to the definition, we already know if the elements all are in the left subtree should be less than the root node, and all the elements in the right subtree should be greater than the root node. Okay, compare the elements first once. 6 less than root node, 4 less than root node, 8 less than root node, 5 less than root node, 10 less than root node. Not only these elements, for these elements, if you take 5, it should be also less than this with this root element. 4, it should be less than this root element. 6, it should be less than this root element. In the same way, check out the right elements, right subtree elements. 19 less than the root element, 17, 43, 31, 49. Likewise. And you have to compare all their root elements also. For example, if we take 31, 31, see, compare with the root node, it is less than the root node. That's why we have placed it to the left side. Okay, first we'll see the example, how to construct a binary search. Okay, I have taken 11 as a root node. Okay, next I'm going to take the next element, 6. Now, where we have to place the 6th element? Compare the 6th element with this root node. It is less than or greater than? Less than. Then where we have to place according to the definition? To the left side of the root node. If it is less than the root node, it should be blindly placed on the left side of the root node. Next, take the next element, 8. It is greater than or less than the root element? Less than the root element. Come to the left side. Left side, already we have inserted one more element, 6. Now compare this 8 with the 6. Now, 8 is greater than the root node. Now it is the root node. Okay. Now where we have to place the root 8? It is greater than the root node means it has placed it to the right side of the root node. Right side of the root node. Next, take the next element, 19. First, compare with the root node. What is this element? 11. 19 is greater than 11. Then where we have to place? If it is greater than the root node, we have to place on the right side. Take the next element, 4. Compare with the root node. It is less than the root node. Then come to the left side. Left side already we have placed 6. Then compare with the 6. If it is less than the root node 6, then where we have to place the 4? Place to the left side. Next, take the next element, 10. Okay, now 10. Compare with the root node here. Okay, it is less than the root node. come to the left side already 6 is placed. Next, compare with this 6, 10, greater than the root node, come to the right side. Already 8 is placed in the right side. And what I'm going to compare with this 8 element with the 10. Okay, if it is greater than the root node or less than the root node, it is greater than the root node. Then we have to place on the right side of the root node. Okay, next, after 5, compare with this root element, less than. Compare this root element, less than. And come to the left side and compare with this element, 4 already inserted. Compare this element. It is greater than the root element. Then where we have placed? To the right side of the root node. Next, what is the next element? 17. Compare with root node, greater than, come to the right side. And already 19 is placed here. Compare with this root node, it is less than the root node. Then where we have placed it? To the left side of the root node. In the same way, 43, greater than root node, come to the right side. Again, greater than this 19, come to the right side. And we have placed it at the right side of this 19. Okay, next, what is the next element? 49. Compare with root node, greater than, compare this node, greater than, and compare with this root node, it is also greater than this 43. Then we have placed it to the right side of the node. In the finally 31, compare this root element, greater than, compare this element, greater than, and compare this element, it is less than. That's why we have placed it to the left side of the element. This is called as a binary search tree. Okay, what does I mean by binary search tree? Is simply all the elements in the left subtree should be less than the root node. All the elements in the right subtree should be greater than the root node. That is called as binary search tree. Okay, now we'll go for the AVL. See, we already know that. First, what is the first point? An AVL tree is a binary search tree. Okay, okay, we have seen what is meant by a binary search tree. Okay, see the definition. In which, how we can say a AVL tree is a tree is an AVL tree means we have to satisfy some conditions here. What is that condition? Means the difference of heights of the left and right subtrees of any node is less than or equal to 1. That means, see, what are the height of those elements means the height of the every node should be equal to -1 or equal to 0 or equal to 1 or less than 0 or less than 1. That's it. This is the condition we have to satisfy. We'll see one example, then you'll get very clarity on that condition. Okay, what is meant by AVL? It is nothing but a combination of two scientists are there who introduced this AVL base. Those scientists are called as Adelson, Welsky, and Landis. That's why we are calling it as a AVL tree. Okay, or it is also called as a height balanced tree. It is also called as a height balanced tree. Okay, how? When we can say a tree is a AVL tree? When we can tell a tree is a AVL tree? That means the every height of the every node in the given tree structure, the every node height balance factor of the given tree structure should satisfy this condition. The height of this means should be less than or equal to -1 or less than 0 or less than 1. Okay, see how to check the balance factor. See here, balance factor equal to, how to check the balance factor of every node in the given structure means balance factor equal to height of the left subtree minus height of the right subtree. Okay, see here. For example, we have taken one tree structure is there. Okay, how many nodes are there? 1, node 1, node 2, node 3, node 4, node 5. We are having 5 nodes in this tree structure. Now we can say this tree is an AVL tree. When we can say a tree is an AVL tree means conformly, we have to confirm that, we have to make sure that when a tree is an AVL tree means all the balance factors of these nodes should be satisfy these values. That means it should be less than -1 or it should be equal to 0 or it should be equal to 1. If all the balance factor of these nodes will satisfy these values, then we can say this tree is an AVL tree. Okay, we'll check the balance factor of every node. We'll check the balance factor of every node. Okay, first node. See, node 1. Okay, balance factor equal to, we already know the formula. That is the condition. What is the balance factor? Height of the left subtree minus height of the right subtree. See here, the height of the left subtree. The height of the left subtree. How to calculate the height of a left subtree means the height from the starting node, root node to the leaf node. The height from the root node to the leaf node. That is called as the height of the left subtree. Okay, see. What is the height from here to here? 1. And here to here? 1. What is the height of the left subtree? 2. See, balance factor equal to height of the left subtree means 2 minus height of the right subtree. Height of the right subtree. What is the height of the right subtree means? Starting from the root node to the leaf node. Okay, what is the height? See, from here to here, one link is there, and here to here, 1. Now, what is the height of the right subtree? It is also 2. 2 minus 2, it is 0. Okay, now there is no any problem. It is under the range of -1, 0, and 1. Now, check out the balance factor of second node. Second node balance factor. See, what is the height of the left subtree? Only one node is there. One leaf node is there. That means how many links are there? Only one. That means 1 minus. Is there any right subtree is there for this node? Root node 2? No. There is no any right subtrays. That is 0. 1 minus 0, 1. It is also within the range of our values. Next, come to the third node. Is there any left subtree? No. Balance factor equal to 0. Is there any right subtree? No. The balance factor is 0. Now, balance factor equal to 0 minus 0. That equal to 0. Next, check out the same way. Fourth node. Left subtree 0 and height of the right subtree -1. 0 minus 1 minus 1. Next, balance factor of fifth node. Balance factor equal to 0 minus 0, that equal to 0. Now check out all the balance factors of the every node in the given structure. 0, 1, 0, -1, 0. That means it all satisfying these values. Now we can say, now conformly we can say that this tree is an AVL tree. This tree is an AVL tree. For example, we'll take some cases are there in this AVL tree, or we can tell it as a what are the rotations in the AVL tree. We are having 4 types of rotations in the AVL tree. Okay, we'll see. For example, case 1. We are taking one example here. 4 cases we can say, or we can say 4 rotations also. Okay, example. We have taken some 3 elements are there, 8, 9, 10. Okay, now we have to construct a binary search tree by using this 8, 9, 10. Why we have to construct a binary search tree? We already told that the first point. What is an AVL tree? AVL tree is a binary search tree. You have to remember that point, very important. Okay. See here. First, I am taking the first element as a root element, and then I am taking the second element, 9. Compare the 9 element with the root element. It is less than or greater than? Greater than. Then where we have to place? To the right side of the root node. Right side of the root node. Next, coming to the next element, 10. Compare with the root element, greater than root node, and come to the right side. Already 9 is there. And compare with this element and place to the right side. Now, what we have to do? If you want to tell the tree is an AVL tree, what is the condition we have to satisfy? We have to check all the balance factors of this tree structure, all the balance factors of every node. If all the balance factors are within the range of -1, 0, and 1, then we can say it is an AVL tree. See, now check out the balance factor of 8. See, what is the height of the left subtree? No any root, no any left subtree is it. That means 0 minus, what is the height of the right subtree? 1, 2. See, this is the leaf node. 0 minus 2. That is equal to, what is the value? -2. Now it is an AVL tree? No, it is not an AVL tree. If it is an AVL tree, the balance factor should be within the range of -1, 0, and 1. Now, how to convert this tree into an AVL tree? Now, how the problem have been occurred here? How the balance factor is not balanced here means by placing one element to the right and placing again element to the right. That means right, right. We can call it as a RR rotation, or we can call it as a RR problem. Okay. Now, how to rectify this RR problem? See, now we have to perform one rotation. We have to perform here. What is that rotation means? Rotate the elements in the anti-clockwise direction. Rotate the elements in the anti-clockwise direction. From where we have to rotate means, see here, from 9. See, keep your showing finger here and your thumb finger here, and rotate the elements in the anti-clockwise direction. That means then 8 comes to the right side of the 9. Okay, see here. Now, what is the root element? 9. And what is the left element? 8. And what is the right element? 10. After making the rotations, you have to make sure that and first check it is a binary search tree or not. We have to check whether it is a binary search tree or not. Okay. Now check out. Now it is the root element. What is the left element? Less than the root element. And what is the right element? Greater than the root element. Now it is a binary search tree. Okay. Now it is a binary search tree. Then when we have to confirm it is an AVL tree, we have to check all the balance factors of every node in the given structure. Okay. Now check the balance factor. Check the balance factor of 9. Left subtree height 1 and right subtree height 1. 1 minus 1. The balance factor is 0. Okay. And for this one, 0, 0. 0 minus 0, 0. And for this one, 0 minus 0, 0. Now check out all the balance factors of every node in the structure. 0, 0, 0. Now we can call it as an AVL. Okay. This is the case 1. Next, coming to the case 2. See, here we have taken one more element, so 3 more elements are there. Okay, now first construct a binary search tree. Taking the first element as a root element. What is the next element? 9. It is less than the root element or greater than the root element? Less than the root element. Then where we have to place according to the binary search tree rule? To the left side of the root element. Next, 8. Compare with the root node, less than, and come to the left side. Already 9 is there. Compare with this element, and again it is less than. Then we have placed it to the left side. Now, we have constructed one binary search tree. Now, check out all the balance factors of every node, starting from the root node. Okay, now take this element, check out the balance factor of this element. What is the height of the left subtree? 2. What is the height of the right subtree? 0. 2 minus 0, it is 2. Now, it is an AVL tree? No. When we can tell a tree is an AVL tree, if it is the balance factor of every node should be equal to minus 1 or equal to 0 or equal to 1. Okay. Now, the problem have been occurred here. Now, how this problem have been occurred, how this balance factor is not balanced by placing one element to the left side and placing one more element to the left side. That means this problem can be called as LL problem, or we can take it as LL rotation. Okay. Now, how to rectify this problem? Before that, RR problem, what we have done, one rotation we have done, that is in the anti-clockwise direction. Take it as a vice versa. Now, for example, what we have to do? Now, rotate these elements in the clockwise direction. Rotate these elements in the clockwise direction. We have to perform one rotation here also. See here, starting from the 9. Keep your thumb finger here and keep your showing finger here and rotate this element to the right side. Okay, see, after rotation, see, 9 is here and we have rotated this element to the right side. Now, after making the rotation, what is the main important point? We have to check it is a binary search tree or not first. Okay, root element, compare with the left element, less than the root element, compare the right element, it is greater than the root element. Now, we can tell it is a binary search tree first. Now, when we have to confirm it is an AVL tree, check out all the balance factors of every node. 1 minus 1, 0, 0 minus 0, 0, 0 minus 0, 0. Now, 0, 0, 0. Now, it is a AVL tree. This is the second problem. Next, coming to the third case. Okay, here we are having 3 elements are there, 10, 12, and 11. Okay, take the first element, root element. Second element, it is greater than the root element, place to the right side. Third element we have taken, compare this element, greater than, and compare this element less than, we have placed it here. Now check out the balance factor of this. Check out the balance factor of this element. See, height of the left subtree 0 minus height of the right subtree. Right subtree means to the leaf node. What is the leaf node in the right structure? This is the leaf node in the right structure. That means 0 minus 1 to 0 minus 2. That equal to minus 2. Now the balance factor is not balanced here. Now how this problem occurred here? By placing one element to the right and by placing one element to the left. Now we can call it as RL problem. For rectifying the RL problem, we have to perform 2 rotations here. We have to perform how many rotations? 2 rotations. First, we have to rotate the elements into RR format first. What is the first rotation we have to do? Rotate that elements to get into the format of RR format. Okay. While making the rotations also, we have to follow the binary search tree rule very carefully. Okay. See here, from 12, I am going to rotate this element to the right side. I am making one rotation here to convert it into the RR format. While rotating these elements, okay, keep your thumb finger here and keep your showing finger here. And now rotate the elements here to here. See, after getting the rotations, 11 will come to this place and 12 will come to the downside of the 11. See here. Now, after making the rotation, now check out the balance factor, check out the binary search tree rule. Root node greater than the root node. Root node greater than the root node. Now it is a binary search tree. Okay. Now what problem it is? RR problem. We already know, we have seen the RR problem. If it is an RR problem, how many rotations we have to perform? One rotation, that is in the anti-clockwise direction. Okay, rotate this element into the anti-clockwise direction. Now what is the root element? 11, left 10 and right 10. Now check out the balance factors of all the nodes. All are 0. Now we can tell it is a Avl tree. Next, one more case is there. Case 4. See, again, we have taken 3 elements, 10, 8, 9. First, construct a binary search tree. 10, root node, 8. Less than root node, place it to the left side, 9. Okay, compare with the root node, it is less than 9 and 8. It is greater than 8. Place it to the right side. Okay, now check out the balance factor of this node first. Okay, it is right subtree. What is the right subtree balance factor? 2 minus, what is the, sorry, left subtree height is 2. And what is the right subtree height? 0. 2 minus 0, 2. Now it is not balanced. Now how this problem occurred? This is called as one element placed to the right, left and one element placed to the right. This is called as LR problem. See, we are calling it as a LR problem, or we can take it as a LR rotation. Okay, now how to rectify this LR problem is here also we have to do 2 rotations here. We have to perform 2 rotations. First, we have to rotate the elements into LL format. Okay, what we have to do? We have to rotate the elements into LL format, taking from the 8. Okay, see, now we have to rotate these 2 elements in the anti-clockwise direction. First, we have to perform these operations as a anti-clockwise direction to make it as a LL problem. Okay, see, keep your thumb finger here and keep your showing finger here and rotate these elements. Okay, if you rotate these elements, see here, 8 came to the down and 9 came to the second place. Now, after making the rotation, make sure that it is an binary search tree rule following or not. It is very important. Okay, 10 root element less than 9, 8 less than root element. Now it is a binary search tree, no problem is there. Now which format here it is? It is in the LL format. We already see that if the problem occurred by placing the elements LL problem, what are the rotations we have done? Clockwise rotation. What is the rotation? Clockwise rotation. See, do the same thing from the 9 and rotate this 8 element to the clockwise direction. Now, after making the rotation, see here 9 and to the 10 came to the right side of the 9. Now, check out all the balance factors of this every node. 1 minus 1, 0, 0 minus 0, 0, and 0 minus 0, 0. Now, it is a Avl tree. Okay, this is known as Avl tree. What is an Avl tree and what are the rotations in the Avl tree? Okay, thank you.